Hi, everybody. So today is the 16th of March, the day before St. Patrick's Day, if anybody besides me cares or marks that sort of thing. But we are starting chapter 6. We've finished our midterm exam. And I bring this up specifically because there is a break in the order. We've done chapters 1 through 4. We're going to do chapter 5 later. We'll do chapter 6 beginning right now. Before we have our quiz in the middle of the second half of the term, we'll do 3 chapters, that's 6, 7, and 8. They're all mathematically related to each other. Some of you may be happy we're back in two-dimensional reasoning again, so that's always a happy thing for some people. And the material that we cover at 6, 7, and 8 are strongly related to what we'll do next year in dynamics and what we'll do next year in mechanics of materials. So we'll do 6, 7, and 8. We'll have a quiz, and then we'll do chapters 5 and 9, and then we'll have the final exam, and we'll be done. The reason that we pull out 5 and 9 is the math involved in chapter 5 and chapter 9 are very similar to each other, so it makes sense to do it this way. So today is March 16th. And by the end of the week, you should have finished chapter 6 and turned in the homework. And then next week is chapter 7. So by the end of next week, even though it says the 16th, it doesn't mean homework 6 is due on the 16th. It means it's due on March 21st, which is Sunday, 7 days from now or 6 days from now, depending on how you count that. Same thing with this. And then we have chapter 8. And then right before the Easter break, you'll do quiz number 2. And we don't call it Easter anymore. We call it the spring holiday, which I find confusing. So I refer to it as the holiday formerly known as Easter. And then we'll come back and we'll finish off with chapters 5 and 9. So whatever you like to call it, we'll do 6, 7, 8 quiz. Should be able to get a 4-day weekend. Then we'll come back and do the rest of it. All right. So when we talk about chapter 6, what we're really talking about is, pull up a PowerPoint. Take a look here. And then I have to see if this is going to share properly. Wouldn't that be nice? I also have too many PowerPoints open. But there we go. All right. So what we're talking about in chapter 6 is the analysis of structures. And the material that we'll do here will lead directly into the material that we'll do for mechanics of materials next year. In fact, when we do statics, and we do analysis of structures, there are 2 main methods that we use here. One is called the method of joints, the other is called the method of sections. We will do a review of those at the beginning of mechanics of materials so that you'll be ready to hit the ground running, so that so we actually have homework assignment over the same material again, so in next year, so that you'll be able to be ready to go.
So all right. This is like the pre-algebra.
Yeah, this is like the pre-algebra of materials. Okay, so we already know that. I was just looking to see if I've got the right screen share. I apologize for just cutting out like that in campus here on camera. Let's go ahead and just do this to make sure. So if we have, when we start talking about the analysis of structures, we already know that if you have summation, in order for something to sit still, you need to have the summation of forces in the x direction equal to 0, the summation of forces in the y direction equal to 0, and you have to have the moments about any point or any axis also equal to 0. So when we have a structure like a truss, we have trusses, frames, machines, but a truss is always built on a triangle. It's always built on 2 force members. What we mean by 2 force members is you have a connection at each of the ends of something. So like this particular thing right here looks a little bit like a truss. It's connected at point E, it's connected at point B, and it's connected at point C, and it has a weight pulling down on it. So this is just like a cross arm or a sign or something like that hanging on it. One of the things, although it seems logical, you start doing the analysis, sometimes you can miss this point, is that if you have a structural member, the force has to be borne along that structural member. There's no other way that that can happen. So when you have a reaction, like right here, there is some kind of a force at A. We divide it up into A sub X and A sub Y, just because that completely describes the force. If you have a weight, it's purely a Y directional force because it's just something responding to the force of gravity, and everything else has to occur along the direction of the structural members. So when you have something like this, any piece of it that is bearing a load or has the potential to bear load is called a structural member, or sometimes they'll call it a two-force member, but just something that is put in place to distribute a load. So like, for example, if you think about this, I'll have some great pictures of bridges, maybe I'll find one for you here, but if you think about it, yes,
I have a quick question.
of course.
A here, is that describing reactionary moments instead of force vectors?
Well, no, this is just forces. We're not talking about moments yet, but A is just that pin. So in other words, this particular structure is just held in place by a pin at point A. So here's the picture of it, and there's the pin.
So A sub Y is like the normal force, right?
A sub Y could be thought of as a normal force. It's
I
really,
guess it's also the addition of, it's the normal plus the tension.
it's, what it really is it's a reaction. If you want to be the most accurate, it's a reaction to all that stuff. So
Everything, so.
yes, exactly. But if you look at the whole structure, the Y forces and the X forces all have to add to zero. And if you look at any individual member or a piece of that member, they're also gonna have to add to zero on that member or on that piece. Because otherwise, something would fly off into infinity.
I'm wondering why there isn't a sub X in this diagram, because I don't see any X forces.
This
That cable is,
X and Y both. Yeah. So think about removing that cable. If this is a pin, what's gonna happen in A? Right? So there must be something going on there. So, and here's the good news. If there isn't something going on there, it will be zero in your calculations. So that's the only time you have to really worry about that is if you have too many unknowns to solve for. So, but very good questions. All right. So this is a truss. A truss is an extraordinarily important structural element. And a truss consists of a few things, only straight line members connected at joints. Okay, so, and I'm going over this really carefully because one of the questions that will come up is sometimes you'll have something that looks like a truss and it's not actually a truss. And if it's not actually a truss, you have to take that into consideration with the analysis. But a truss, straight line members only connected to joints. Joints are where two things come together.
so an arch is not a truss.
Some arches are not a true arch, but there are some types of trusses that approach an arch-like shape. But yeah, the other thing is they're always built on triangles. Okay, a triangle is basically if you squish it or you pull on it, it doesn't lose its shape until it loses structural integrity. Other shapes you can't say that about. Okay, the other thing is that the force is either pull or push on the structural members. So the elements of the truss are called structural members. Where they come together are called joints, and where they come in contact with something else are the reactions. Okay, but as I had said before, the direction of the load borne in a structural member has to be along the structural member. So that means it can only either be in tension or in compression. And whether it's in tension or compression, is a big deal. So the other thing you might see is like, yeah, if you analyze something like this here at point C, and if it's in tension, the force here is going to point upward and outward. It's going to point downward and outward here. Because if these forces do oppose each other, what would happen to that structural member? it would sail off into oblivion. So it's a little bit different way to think about it. When you look at at a joint, think about whether the force is pushing into it or pulling away from it. When you overall member, it's either in tension, you pull apart, or in compression.
If A to B was a single member instead of jointed at D, wouldn't that be, what force would that be?
That would not be a truss. As soon as you put that together, if this is continuous and there's something there, it's no longer a truss. So it's something else. It's a frame or a machine or something else. So
it has to have a jointed D.
yes, only two first members. Bolted or welded connections are assumed to be pinned together. Forces acting member reduced to a single force. Okay, so that's kind of the question that you're asking. And it does happen, but it's just like, that's not what we're talking about today. Which is the answer that I seem to give a lot in this class.
So A and P, or A and D, and B and D are both in compression in this case, because
Maybe. To me, I mean, they'll either be, no, they could be both. Let me show you some more trusses and we'll take a look at this, okay? Here are some different types of trusses. Let me pull this up. Will let me do it. Okay. These are common. I am gonna pull up a picture of a bridge in just a moment here. But these are common types of trusses. And just what I want you to notice for today, when you're talking about the roof trusses, Pratt, Howes, and Finks. Bridge trusses, Pratt, Howe, Warren, Baltimore, Case. This Warren truss is extremely common. You'll see it all over the place. Or other types, stadium truss, cantilever position, cantilever portion of some truss or vascular truss. All of them are built on triangles. If you look at the basic shape that you add on to, everything is a triangle. You start with a triangle, add structural members that again form a triangle. So there's lots of, in other words, a truss is very particular. What a truss does is it distributes a load and prevents things from collapsing. For example, if you think about a bridge, in one way, you could say, if you need to get across the stream, you could just lay a board out, right? But what happens to the board? It gets, yes, it gets very bowed in the middle. So if you put a truss on it, then it doesn't do that as much. I want to show you a couple of bridges. Keep going.
Directing
Mhm.
downward force. to
Yes.
Press the.
Yes, yes, you are distributing the load, you are redirecting is correct on both, so. Let's see. Here we go. Ha,
You ever seen pictures of the frame inside of the Hindenburg or any dirigible?
oh yeah, the blimp, the dirigible, those are extremely, those are super.
Trusses that approximate a circle.
Yes, yes, you can do all kinds of things with the truss. One of the things I love to do whenever I go anywhere is to take pictures of things that are interesting to me. And this is a bridge called the Mackinac Bridge, or the Mackinac Bridge is how it's spelled, but it connects the mitten of Michigan to the Upper Peninsula. And it's one of the longest suspension bridges in the United States, possibly in the world. But what you'll see is there's a long run up where we have pylons. And then I assume the water gets too deep to consider with the pylons. So we just have two towers. And then you have a bunch of strings hanging from that support the bridge. So in its natural position, a suspension bridge bows upward, because then when the weight of the cars goes across it, it bows it back down again. So that's how it's cool. This is a very typical Warren Truss bridge. And these are built, they're still very functional, but in olden times, they were very common, especially for shorter spans, but they're easy to construct. The triangles are mostly equilateral, so all the building material can be about the same size. So there's lots of neat reasons to do a Warren Truss. This is a more local bridge. Oh, I love that one too. This is the Willwood Bridge. it'll come up, there it is. This goes across, this is actually south of town. It's just south and west of town. And you can see the trusses on that bridge. This is actually a functional diversion dam that irrigates the Willwood Irrigation Project. But you can see, right now you don't drive across the dam, but for decades, the road went right across the dam. So I took this picture to kind of show what that looks like, but you can see it's a heavily structured bridge designed to carry quite a bit of weight. It's very narrow compared to stuff that we need today. And at the edge of the Willwood Dam, there's me just jumping out of my car to go get a picture. They have these expansion joints because not only due to heat and cold, the bridge expands and contracts, but also about the weight that's on the bridge, it will expand. And so you need to have something that will take that load without splitting the bridge, without, making it combust. And bridges tend to be built out of concrete, some of them are built out of steel, but old bridges tend to be concrete, and it's very unforgiving intention. So you need to have something to make sure that you stay in compression forever, as long as you possibly
What
can.
are those pieces of?
These,
Yeah,
that's metal. So like there's a concrete slab here, and then a gap, and then another concrete slab. And then they're connected with metal.
are there pins inside? Like what's the?
Oh, I would imagine there's some sort of a connection. I don't know what it is, but nobody's let me climb inside to see. I've been inside the Willwood Dam, but I've never gotten to get to see much about the bridge itself. This is so cool. This is called the Millennial Eye Bridge. This is at Newcastle upon Tyne in England. And I've actually gotten to see this. But one of the things that happens here is, as a desert dweller, I know I have almost no vocabulary for humongous amounts of water. But what the Millennial Eye Bridge does is it rotates up. It's like a drop antenna for Mr. Boat to go underneath. So basically what happens is, it's like in the old days, they would have drawbridges when a ship would come through. And now, and they still do that. This is just a footbridge. It's a walking bridge, but it rotates upward so that the ships and boats can go underneath it because of commerce. So, but it's also really cool. You can't see in this video, but there's all these old bridges, like turrets, bridges that look like the Tower of London stuff. And yeah, so it looks like this. See, these are the kind of things you can do as an engineer. So,
That seems more,
oh, there's the old bridge. Sorry, what's that?
yeah.
I wanted to hear what you said, but I got excited because you could see the old bridge in the background.
That too. I was just thinking, like, this seems more performative than functional. 'Cause
It is.
If I was put in charge of making the most efficient
Yep.
way to solve that, I just do that.
Yes.
That just stays up. Like, why does it need to go up and down? You can't use it while it's in its up position.
Yes, you can't.
Everyone who wants
exactly.
to walk across it now has to wait
Yes.
for the boat.
It's really funny in Europe. Now, you've been to Ireland, right? So, Ricardo, have you ever traveled to Europe? Okay, so I've never traveled in Honduras. The only place I've ever been is Raton, which is beautiful, but in Europe, it's so, the structures are so old that it's almost like here is like everybody wants to sort of maintain architectural harmony and keep everything looking the same. It's more like, if you ever go to the Louvre, which is the big art museum in Paris, it's like, it's this old castle looking building, and then it has like a glass pyramid on the top of it, and it's like, I mean, from my eye, it looks really discordant, like this looks discordant, but I think what they're really saying is, look at this contrast and look how long we've been here,
Yeah.
so it's, and like, yeah, you look, when you're in Newcastle upon Tyne, Newcastle was bombed unmercifully in World War II because it was the industrial heart of England. And all the shipyards are there, but like, you can just go over here on this walkway and just look off to the east, and you can just see like humongous ships out. I mean, just in dry dock, being built out there. So it's a place of contrast, I guess. But yeah, I agree. I think this looks discordant. I mean, I'm fascinated by it, but it looks discordant to me. So yeah, there's lots of cool things like that.
I'm wondering about the forces on those motors now. Cause like, the footbridge looks heavier than than the ring on top. The ring on
Oh,
top looks really
sure.
light. So that
Well-
means it has to just kind of brute force it up there.
It might.
It's not counterbalancing that much.
Well, if you look at it. I kind of think this is longer than this. So I think that you get more moment because of where the weight distribution on this. But I understand what you're saying, like if it were perfectly balanced, it would require less power. You know, it's kind of like, here's another one. This has nothing to do with this class, and then I'm gonna go back and talk a little bit more about our class.
But even then, you still have to get it up to the tipping moment for it to have that leverage.
Yes. So. Okay. So, let's look at these fellas.
I'm very familiar. It's just not on my other side of the house.
Okay, so one of the things that you find out about this is, like, when you look at this. It pivots here and the motor's back here. This is a drill string, which is thousands of feet long, possibly. And carry up a part of column oil in it, so it's quite heavy. So if you look over here. You have counterweights, and the counterweights are set so that the moment for the counterweight balances the moment from the pumping unit, the drill string. And if you don't, if you live close to these, you know this for a fact, you'll hear it, like the motor will go, because it's out of balance. And so every time it has to pick up the drill string, it has to pull really hard. If you just listen to them, and you can hear a balance just go like that, and you know that you've got a good balance, and you just have to change the position and the weight of the counterweights to make that happen, so.
Now, if it's carrying the column of oil, that also means that it's much heavier all the way up than down.
Well, no, okay, so what it does, this is a mechanical engineering question. It pushes the oil off to the side, so if you think of this is kind of how it works. Is you have this very long drill stem. And then at the bottom, you have a rod pump, okay? But up here, you have tubing, so you have a bigger hole than the rod and the pump. Sometimes you have a tubing pump, but in general, it goes through it like that. Then you have what's called an annular space. So what you really do, this is about 30 feet long. So you actually pull about 30 feet of oil into the rod pump on the upstroke, okay? But on the downstroke, you push it over into that annular space. So it's no longer pulling it up, it's pushing it up. So the oil that you put into this pushes the oil that's ahead of it up through the annular space. So it's really ingenious for removing weight, and also in general, it's hard to pump. Well, you can only pump to a certain limit, which we'll talk about in fluid dynamics, but so you can't pump against a vacuum. You can only pump against whatever is pumping
Only
against.
sucks about 30 feet.
That's exactly, it is, and you know what 30 is? Oh, this is great. 30, the hydrostatic gradient is 0.433 PSI per foot. So if you multiply those two numbers together, you get 30 feet times 0.433, which is 12.99 PSI. Well, guess what atmospheric pressure is? So this is this minus some friction. Isn't that cool? So yeah, and here we don't even have 14.7 PSI, so we can't even downhole you can, but up in this atmosphere, you can
So
only pull about
lower
20
like
feet.
Death Valley, we could suck higher.
Yes, that's right. Isn't that great? So very fun. See all the fun you're gonna have in all these engineering science
Yeah.
classes? So anyway,
I've been wondering about pumping because
yeah.
I've had an idea of like, what if I wanted to use a windmill to pump water?
Oh, yeah, it's
So
easy.
I would need something that goes, this kind of solves that problem because it's pushing.
Yes. Yeah, you need to devise a downhole pump so that you push instead of pull. You can also use a downhole electrical pump, which is they just call them Ritas. Rita is just one variety of those, but they're very expensive. And these are kind of like a tried and true thing.
So
But-
that's 30 feet long, how wide is it?
Depends. Usually the tubing is 5 7/8, so it has to be smaller than 5 7/8. So,
So it'd be hard to put a motor.
yeah, yeah, you can put a motor down hole and you can pump it up with a Rita pump. But they're basically on a, I mean, I'm exaggerating, they're on a very long extension cord, and so there's some issues with that as well, but they're very cool.
Get like resistance over distance.
Yes, yes, and, but. Pumping unit, okay, so. Using a windmill to pump, like to fill a stock tank is a great idea. And what basically happens is because once you dump the water into the stock tank, you're not asking for more power from the windmill and you're not burdening whatever mechanism you're doing. So your pump can be driven by the wind turbine, and then the water is just sort of like a secondary feature. I mean, that's what you really want, but as far as the mechanism goes, the water and filling the stock tank is a secondary feature, so it's the best application ever. It's just the best application ever, so, yeah, pretty cool, huh? See all the things? So anyway, when we start, let's go back to our PowerPoints and take a look at a couple more, okay? And I think I have this pulled up like 15 times, so I keep going back to some other things, so that's okay. All right, here we go with simple trusses. A simple truss is constructed by successively adding 2 members and 1 connection to a basic triangle. A rigid truss will not collapse. So if you look at the 2 pictures, this based on a triangle, if you push on it, it'll start to bulge out a little bit, but until these actually rupture, it's going to stay the shape of a triangle. If you have a 4-sided object, if you push on the B, it's actually going to splay and collapse. So that's why trusses are built on triangles. So pretty cool, I think. And then I just show you how to build up different kinds of trusses, although most trusses in this world are not, they don't look like this. I
So
mean,
that square is rigid because of the frame inside of it.
yes, and if you do the math on it, this is the way that it works out, but. I don't like this truss very much, but that's,
It's not symmetrical.
no, that's right, it's not symmetrical, is right, so. So the first thing that we're going to learn, and we'll have a few minutes left, so we're not gonna do any problems today, we'll be on the videos for you, but is the method of joints. So here's the basic thing, there are 2 methods that we're gonna learn in here that will also carry over directly into mechanics and materials for you. The method of joints says this. If you consider a joint just as this pin that connects different members of the truss. If you consider any point, like let's look at point D, okay, right here. And you say, I have a structural member going into it like this. I have a structural member going into it like this. I have a structural member going into it like this. And I have a weight pulling down on it, okay? The method of joint says if you just look at this joint as being the center of the universe, and you consider all of these things, forces acting on it, that they will exactly balance out, so that going into that joint, the forces going into the pin at point D in all vector directions have to sum up to 0. So that means that if I look at this force and this force, those are the only 2 x-directional forces, right? If you look at point D, you can see that this is going to have to equal this because these are purely y. And also see that this is going to have to purely equal this. Okay, what that means is everything here is pulling on this joint. And if you think about it, what that's saying is this is going to be in tension, this is going to be in tension, this is going to be in tension, and that's not tension or compression because it's just a weight, right? But how do you work out a problem like this? You just break things into components and solve for them just like anything else. Look at point B for a moment. We're told at point B that we have a force that looks like this, and a force that looks like this, and a force that looks like this. All right, now here's the deal. this is a Y directional force. This does not have a Y component, so the Y component of this has to equal this. That also means that this is pushing up, this is gonna have to push down. Also, if this is pushing to this side, now this is the only one that has an X, if it's pushing to the right, this has to be pulling to the X. So you've already to the left. So you can already identify the direction of all those forces. Then how do you do the work?
Summation is just converted a lot vertical component into a tension.
It is.
Into the member.
Yep, that's exactly right. So here, let me say this is positive, right? The reaction at B is positive, minus, it's going down. What is this number, C? The force in CB that's in the Y direction. Those two things added together equals 0. In the X direction, this is BD. It's negative force in BD. Plus the portion of the force CB that's in the X direction. Those two things have to equal 0. And how can we resolve this? Trigonometry. We can find this angle right here. Based on lengths, or maybe sometimes you're given an angle, and then you're ready to go. So this is the method of joints, and this is what we're gonna work on first. So I have just a couple minutes left. You can have more complicated trusses, but they all work exactly the same way. And the method of joints always works the same way.
Noticing we also really prefer right triangles, which is convenient for us.
They like, that's not common. I think that's just the way these are drawn. So you get all kinds of triangles, like, yeah, exactly. So here's problem 6.1. We have reactions at C and E. Oh, I have one more piece of code to show you here. And then we have two applied forces, and then we have the internal responses of the structural members. All right, if you look at this support and you look at this support, this has rollers on it. This is a picture of a support that has rollers. What that means is it's not going to bear anything in the X direction. It's only going to bear things in the Y direction. This is a fixed support, meaning it will bear X or Y. So there's going to be a reaction at C in the X and a reaction at C in the Y possibly, but at E, there's only a reaction in the Y direction. So this is code in your author speak for saying this does not bear an X directional force. This is code for saying it can bear in both directions.
That's really fascinating because we could make a support
Mhm.
and then just force you to carry all of that.
Yes, you could.
That's what you vote.
Uh-huh,
Wow.
I know. Pretty cool, huh? So let's take a look at what the math looks like in the couple minutes we have left here. Okay. For this one, the first thing you have to do is to solve for the externals, okay? So we have like I said, you have reactions here in the X and Y, and you have a reaction here in the Y only. Then you have two Y dimensional forces. So they want to solve for CY, CX, and E. And they do that using, you have three unknowns, so how many equations do you need? 3. So you take the external forces on the truss, and you find those reactions to begin with. Then you turn inward and take a look at what's going on at different joints. They start with joint A, and they say there's a 2,000 pound force here, some force here, and some force here. This one has an X and Y component. This has only an X. Since this is only Y, the Y component of this has to be equal and opposite to that, right? So the force in AD has to be pushing on the joint because this is going down and this has to be going up. That means pushing on the joint. That means compression. FAB right here. Okay, if this is going up, that means that this is coming to the right because this one's going to the left. And so it's going to be pulling on the joint, which is tension. So the way that you determine whether it's tension or compression when you're using method of joints, you decide that internal force is pulling on the joint, tension, or pushing on the joint, compression. Those are only two choices you have. But it's a third of your answer. Number, unit, tension, or compression. All right, so do you guys have any questions at this point? All right. Well,
So is it just like intuition? I can see that the moment would be the clockwise direction because of where the force being applied.
That's a good question. Yes, you can use intuition. If you don't see it, I would recommend you always make it positive. Because then, if it's not correct, it'll come out as a negative. If you choose it as a negative and it's not correct, it will come out as a negative, which means it's positive. That's just it. That's just asking for trouble, in my opinion. So if you know what it looks like, use that. If you don't, assume it's positive. And once you start something and you think to yourself, oh boy, I chose that wrong, do not change it midstream. Unless you want to go back to the very beginning and change it at the very beginning. Because if you do, if you change it in mid-course, it's just a chance to confuse the issue and get the wrong number.
And theoretically, if you keep all your signs consistent
Yes,
with each other,
yes,
you'll still get an answer.
absolutely, 100%. So the method of joints is really kind of fun to do. It's, I don't want to say relaxing, but it is kind of like meditative. Yes.
Do you have to do every joint in a problem like that?
Well, they'll ask you for certain things and then you decide what you need to do.
So you don't always have to do everything.
Right. They can't, yeah.
Necessary.
They can ask you to analyze the whole truss, or they can just ask you to find the force or the tension and compression in a particular member. And so the first method we're going to use is a method of joints, which is very, very handy. Later on, in just a couple, probably very soon, we'll start using something called the method of sections, which they both do the same thing, but one of them will work better in certain applications than others. So try to keep an open mind. How's that sound? All right. All right, guys, that's it for today. I'll be in my office. Ricardo, let's set an appointment to go over your exam and we'll do that. So